So welcome everybody to this awesome talk. We are going to unveil the deepest and dirtiest secrets about the JDK, so be prepared. Do not rush, as I said before. So talk is about a scalability issue. So that's how the name, cracking the scalability wall. So first, I'm Francesco Nigro. I work as a performance engineer, principal software engineer in Red Hat. I'm the performance lead of Quarkus. And I've been an open source contributor for quite a long time in different projects that care about performance. I'm PMC and lead of Apache ActiveMQ Artemis, and I love performance stuff, as you can expect. So, Sanne.
Okay. Hello, everyone. I'm also a software engineer at Red Hat. I'm the architect and the technical lead for the Hibernate team and projects. I was also in the early prototyping, and when we were developing Quarkus, before deciding it was actually worth doing a project. I'm still involved with Quarkus research and development. My role is not directly related to performance, but I'm very interested in performance, and of course the Quarkus aspect makes it all very interesting. I also contribute to many other open source projects, which are too long to list. But so let's get started with this issue. We were trying to ensure that all of the work we have done to make Quarkus very efficient and fast to start was also actually very fast runtime. And we don't care as much to start fast if it's then not able to perform really well at runtime. Right? And we have been using several benchmarks. Now, one of the most puzzling ones was the Tech Empower benchmark. Now, this was interesting for us because even if it makes some questionable choices, like things that we don't necessarily agree with, the beauty of Tech Empower is first, it is an independent group. It's not that we are deciding what to test and what to verify so we can show nice numbers in a particular use case. But it's really what a lot of people together in bug discussions have decided are interesting metrics for a framework or a runtime. The other aspect which is interesting is that the Tech Empower benchmarks are not JVM specific or Java specific. They span all the various frameworks, official frameworks, prototypes, things which are production ready or things which are more like toys to prove some conceptual ideas. This was interesting for us because when we started Quarkus, the idea was not so much to challenge existing other JVM frameworks, but it was more thinking is it possible, is there a future for Java-based languages in a cloud future? So we are actually actively trying to compete also with Go and Rust and potentially JavaScript, other languages and frameworks, even things written in C. So it is interesting for us to see, well, can we perform as well as the best of the league in the whole industry, not just comparing ourselves with existing other JVM runtimes. We, of course, want to compare with JVM runtimes as well, but that wasn't really the sole point, right? So that's making it interesting. Another aspect you need to know about the Tech Empower benchmarks is it has different use cases and different scenarios. So it does have different tests, the JSON serialization, a single query, multiple queries. Each of these have rules and specifications and are validated so that nobody can cheat too much, because badly we figured out that some people are cheating because not everything is being tested. And we figured this out when we try to figure out, hey, how is it possible that they are really beating us in this particular case? And we try to look better in those. So how it looks like, if you go to one of these links, you can have a view. And this is the composite framework scores. This gives you a summary of who's best currently, but it's a weighted score. It might not really reflect languages you want to use or use cases that you care about, but it's a nice site because you can filter it in various ways. So you can focus on particular languages or stacks and see how they compare and how they compare on different use cases. Now, what we would love to see there is, of course, Quarkus to be at the top in every category, right? But that wasn't really the case. Quarkus, actually, when we started this exercise, was performing really low. And that's why they got our attention. Hey, what's going on there? So you start to profile and you start to look into things. Now, the first things that we discovered was, of course, very silly mistakes in our code. And we get those fixed. But then we still didn't really get like in the top 10 even. Like, and there was something really puzzling and annoying, like, oh, actually not many JVM-based things were in the top. And we really like our stack, and we know that theoretically the JVM is an amazing piece of engineering with so many interesting optimizations there that it should totally be possible for a JVM application to be in the very top league, right? Not somewhere in the middle, like of half the throughput of any other player. So one thing we looked at is like, well, CPU metrics, that's one of the first things you start looking at, like what is the bottleneck in our system? In this benchmark, we were seeing like, well, both the Quarkus rest-easy reactive, hibernate reactive, which is one of the particular configurations we were testing, which means it's Quarkus running with rest-easy reactive endpoint and the hibernate reactive engine to talk to the database. And we also care about Vertex, because it is our same team that created the Vertex project, and actually the Vertex technology is one of the founding and the core components within the Quarkus stack. So it's interesting for us sometimes to compare, because something might affect one but not the other, and that gives us a clue about what could be the difference. Now, both of them are totally saturated in CPU usage. So, the bottlenecks aren't really network or things. We know it was CPU. Still, it wasn't really on the top. So there is something happening at CPU level that wasn't allowing us to perform as well as we want. Now, this is the same benchmark being run into slightly different configurations. Actually, not configurations. It's like exactly the same hardware, the same thing. In one case, we call this the not isolated case. We were able to get 1.8 million requests per second. This is on the plain text, so it's a very simple benchmark. It's just hitting the endpoint, and it's expecting to return hello world from the HTTP server. Right? There is no database, nothing happening behind the scenes. So we were having 1.8 million requests per second, but if you were running multiple tests, and then you run another test, then you pause it, you let it rest a bit, and GC, and then you run the other one. That's the not isolated case. So if we were running different tests, but without like restarting the machine or things, the difference in performance was totally wild. Like we go from 1.8 to 4 million requests, like more than double. And this was entirely reproducible, but what is it? Noise, different JVM, JIT compilation decisions? Not really, because it wasn't really luck. It was, after running this many times, it was really clear that it was depending on if you ran another test before that was completely affecting the performance of the sim. So, why is it happening? The next step is, of course, so we look into frame graphs or other profiling data, which is going deeper, right? And what we see in the not isolated run is this, that line which is highlighted there. That's the netty HTTP handling. That's where the incoming package at the HTTP level is, the first processing endpoint. And this is the not isolated one, so it's the one that's performing really bad. And in a flame graph, we're not going to read this in detail. The one thing you need to know is that the more width you have, the more you're spending time on that method. So when the bar is very large, you're spending a lot of time processing that particular set of instructions. It doesn't really tell you why, right? But it gives you a very good clue about like where do we need to look closer. In the isolated run, this is the flame graph you get from it. That same bar of netty, you see how it changes completely. Like it's spending like 4 times, visually it looks like it's spending 4 times more CPU doing the exact same operation. The Java code didn't change, nothing in the server configuration changes. And there is this additional puzzling thing, like what's going on over there? If you look there, that's still netty, but there is no parent in the stack. Like what you're seeing here is pretty much like a stack trace with a weighted aspect of like how much time you're spending in each of those stacks. And there is something going on oddly there that, we can just discard as like, well, the tools, profiling tools aren't always perfect. Like they don't, sometimes something doesn't really add up. But, still puzzling there. So the question was, well, did we break the profiler? Like, is it something out there?
Close the door now is
we
the
close
assembly
the door.
time.
Yes. Nobody can leave anymore. So yeah, you go deeper. You start looking into, those break-in frames. Where are they coming from? And we had some hints. And then eventually, Francesco had the idea. Well, let's use Alexei Shipilev's perfasm, which is a tool to generate assembly code, but from JMH. It's meant for JMH. So he was abusing of this tool to use it in a bit of a different scenario, because we really needed to see what's happening. It's the same bytecode. But what's different is then really the instructions that are generated behind the scenes. So Francesco with Andrew Haley, who's the lead of the OpenJDK team within Red Hat, they have been reading like 20,000 lines of assembly code just to, they were, not all the other tools had failed. Like all the other profiling tools hadn't been able to give us a clue of what was going on. So they just read through all the assembly to see if they spot something suspicious, of course, comparing, the assemblies generated by one and the other configuration. And they eventually figure out that this repen z scas instruction gets their attention. And Andrew is like, oh, I know where that is. And Francesco also, like, you just grab the source code. There is a single point in the whole JDK, so there is a bit of luck that this is used, which is this linear scan. And let's not go too much into this, but this is the piece of code in the JVM, this is in the class object in C. So, of course, hotspot is written in C. It's not written in Java. It's executing Java code. But the code here, what we see is C. And there are these two lines which are of very big interest for this talk. Like the first one is this class pointer, which is pointing to the secondary super cache. Now, the secondary super means it's an interface. Now, that's in the terminology of the hotspot source code. Interfaces are called secondary supertypes. It's not like the main primary type, which is inheritance, so extending from a concrete type. The secondary super cache is the interface. Now, when a class is defined in the JVM, you might have, of course, multiple interfaces. And this list of multiple interfaces is what we have in this array there. That's the secondary supers. So that's the list of all the interfaces implemented by a concrete type, right? So you have one of these structures for every class that's defined in your JVM. The secondary super cache is a single field cache. This is storing the last interface as a particular object has been tested for. And we're going to see more in practice what this means. So we have a little animation here. Imagine you have a piece of code like this. Now, this is a little bit of pseudocode, but we just simplified a little bit some patterns which are very frequently actually used in many libraries that you're using, and maybe even in your own code. So imagine that you have a type. The particular type isn't really known by the code, so it might be an object or something that's implemented by many interfaces, many types, and then it's tested for maybe comparable, and then tested for serializable. Now that's the hypothesis. What's happening? So when you go to the first check there, is instance of a comparable? Now that secondary supertype cache field is null at the beginning, right? It hasn't been tested ever for something. Now, as soon as we say, is it comparable? It's going to, go in the cache. It's null, so I don't really know. I can't use the cache. Let's go in that list, right? And then you might say, we're using an example here. Like, imagine this is an integer object, like the wrapper, not the primitive. So an integer is, of course, comparable. It's also serializable, right? It's also a number. It has multiple interfaces. So it's a common object. Like everybody might be using an integer, and it is comparable and serializable. So it's not completely alien code here. Now, it's checking for comparable. We look into the list of interfaces, and it's yes. But then we store it in the cache, because that's an interesting information that might be useful again. And then it gets casted to comparable, because you want to use it as a comparable. It's going to leverage the cache. OK, good. It's still comparable. You have a cache hit, and that's good for you. So you don't need to traverse that list a second time. Now, you're checking if it's a serializable next. Now, it was comparable in there, so that's a cache failure. We go in the list, and then it's storing now serializable in that cache again. So that next time, if it's serializable, I have an advantage, and then you cast it to serializable. And it can leverage the cache, and it goes through that. Now, the problem with this is that this single element cache isn't really stable over time at all, right? You just need a piece of code which is testing the same object type for one type for one's interface and then a different interface. And this cache is starting to flip-flop, and we call it like ping-ponging. Now, in the Netty source code, this is a very common idiom. This is actual production code that you will find in Netty if you're running Netty anywhere. It's doing this message instance of HTTP. In that case, it needs to do some other checks. And then, oh, but if it's an HTTP content, then there is something else that needs to happen. So every time this encode method is invoked, you are checking first for one interface and then checking for the other interface, and you are storing one, storing the other into this cache, and not actually benefiting much from that cache. So is it a big problem? You might wonder, well, why are you talking about it? It's a single optimization just to not go through that list, right? Now, this is having a pimcom state of this cache, right? And we have seen this class is a singleton, right? This is representing all the integer types in your whole system. They're all sharing the same state, which is the same class instance with a k, right? What about concurrency? What if you have multiple threads going through one of these pipes? They are invalidating each other's caches all the time. And the interleaving of operations might make it a bit randomic if you're like hitting the cache or actually getting in the slow path. So you're getting a bit of indeterministic performance, which is one problem. But the biggest problem is how CPUs are architected nowadays. You are very fast at operating on cache, which is in your L1 cache. You are a bit slower in L2 and maybe L3, but also you tend to share L2 maybe with a peer cache, which is in a very close physical representation, or L3, which is a larger representation. So what's happening here is every time you're writing in one of these fields, and anybody else needs to read that field, and we have seen you're constantly reading that field because you need to know if it's the right type. All the other processors, they need to ensure consistent view of this data across all the cores of your system. The more cores you have, the bigger problem you have, because there needs to be a strong coherency protocol running across these cores. It gets more complicated with modern processors because you have non-uniform memory access. So not all memory has the same distance and delay, latency to get this information. And you have this on writes on the cache, but you especially have it on reads. Like every time somebody needs to read this information, it needs to ensure that this hasn't been written at the same time. Now here we have a screenshot from an article on Anantech, which is showcasing like the latency from each core you have with another core in a package in a Ryzen 7 9050, which is a consumer CPU. Like these things start to be very common nowadays. Everybody has access to these things. This is not just some elite particular region. What's interesting is Ryzen actually has multiple CPU packages packed within the same socket thing. So while it is a physical socket, it's actually multiple groups of CPUs which have distance, and they are wired together with some kind of fabric. And so there are some processors that are able to talk with their neighbor at a very high speed or like low latency. But between some other cores, the cost might be different. So you're also exposing yourself to a very high variability of this latency that needs to happen between these core communications. And here gets the biggest problem. We're also affected by false sharing. Now, what is false sharing? Little explanation first. When two of these CPUs need to have a coherent state among each other, the unit of communication among this is the cache line. So you can't read a single field state from another CPU. You need to read an entire cache line, or write an entire cache line, or invalidate an entire cache line of another core. So if the socket 0 is writing on, say, the first element of a cache line, that's invalidating the whole cache line for the purposes of the coherency protocol. Like the other CPUs, they will not be able to read anything of that cache line. So if the socket 1 here, the thread 1, needs to read a different field, but it happens to be in that same cache line, that's in not valid, and they both need to go through the whole expensive coherency protocol, which is fairly interesting, but beyond this scope. So we're leaving it there. So what's happening is that every time you're writing into that secondary super cache, it's not just a secondary super cache field that's a problem of performance. You're also making it way more expensive to read anything that's close to it. And that secondary super list is the next field. You have a very high chance, depending on how the randomization of the addresses are happening, that those two fields are actually stored in the same cache line. So every time you're failing to read or actually anybody of all your CPUs is writing into secondary super cache, everybody else not only cannot read that cache, they also cannot read the entire list they need to go through as a fallback of the slow path. Now, how to identify if you're affected by this? There is this perf tool, the CTC tool, there is a fantastic blog over there that explains how to use it. This is, of course, system-level things. There also is a very interesting blog post for Netflix engineering, in which they kind of stumbled on the same problem that we identified, but from a different angle. They were noticing that approximately 1/8 of their servers was performing much better than all the other ones. Now, 1/8 happens to be the chance within the randomization of things that those two fields happen to be on the same cache line rather than separated into different cache lines. So what could you do to fix your performance? Well, reboot the server and try your luck again. That could be one approach.
Roll the dice. I mean.
And so let's recap the problem a bit. We have a problem of true sharing. Like this cache is a single point, and it's actually not very effective because it's changing all the time, and you're not really caching the data you need. You're not able to exploit it as much as it was probably designed for. And you have this false sharing problem, and then the NUMA architecture and everything in the physical world makes this all much more complicated to deal with. Now, very interestingly, this was an open issue already. This was already reported officially on the OpenJDK issue tracker by John Rose, who's none else than the lead architect of the JVM, of the hotspot. He reported in 2017, but apparently from notes of implementation in Java, this issue has been there since always. Since Java was created, there are notes from the very same John Rose saying, well, we're going to design it this way, it shouldn't be a problem. And he probably was right. At the time, not everybody had 64 cores in a consumer thing, but also that we noticed as middleware engineers that the OpenJDK team didn't really expect that we would go nuts with interfaces because at the time C was popular, and you would see in C you would refrain from using a multiple interface. It was considered a bad design smell. So why would people do it in Java? Well, we see today that it's very, very common in all the libraries. So it's always been there, this problem, and you don't really see it. So let's see what Franz did about this for Netty.
As the very first slide in which I talk about the various open source projects I contribute for, I mentioned Netty committer. So being a Netty committer, I get the chance to fix it, actually, in Netty. So we discover what was the problem, and now we get the chance to fix it with some horrible code. So I want to report the comments that are not very good, actually, about how the code was bad. I just reported the good things, and you can just look at the bars now without looking at the number. Just trust me, there is a huge improvement, and that one was just related to the HTTP part. Then, it's like guacamole, right? Guacamole. And with guacamole, you find one and you fix it, and then you have another one. The second one was even worse from a Java community perspective, because it was not related to HTTP. So it was related about the Netty pipeline traversal that is basically used always. And Netty is from Java 1.6 exists. Yes, the bug of the JDK was older, but it's not a challenge. No one win. So we fix it, and that's the kind of improvement we got on Quarkus. So it's 3 times in a row. It's definitely worthy with horrible code. Not just horrible code, because it was even worse. We spent tons of hours trying to analyzing these kind of things. I've gone to the therapist later. And the thing is that I talk with my wife, I still remember it, and I say, please make me blind. No, blind is off policy. Take my eyes out. No one has done it. So we decided for a different route. The route was, let's make a rule, no, not a rule, a tool to rule them all. This tool has been a bytecode manipulation tool, is an agent, is built by using a byte buddy from Raphael. So search Raphael on Twitter, you will find him. And the good things of this tool is that has allowed the old things about fixing it to scale at Java community level, not just inside the Red Hat company. So this is open source, everyone can use it. It produces a report, and this report can be used to fix it without learning assembly, go to the therapist, or just make the blind people. So what has happened right after was totally unexpected, or, I mean, we kind of expected it, really. We opened the Pandora's box. So this is just a short list, believe me, of the library that were affected directly, not transitively. So, because, you use Netty, everyone that uses Netty is affected. No, it's not that easy. Everyone was affected. And the very last one is pretty scary. So it's a Java class library. That means that everyone uses it. So, and as Sanne told, there is a JDK issue already open from a long time, and there is a reproducer. So we are going through this reproducer just to show you how the report looks like. So it's not nearly similar to any production code unless you really hate yourself and your mates. So what's doing this is that you have two concrete type, B and C, and they both implement I3. That is a kind of marker interface that implement both I1 and I2. Then you have two methods, foo and goo, that doesn't do anything interesting, actually. They just biased the secondary super cache mentioned by Sanne in one direction toward I1 or I2, depending what kind of type they are being passed as an actual parameter. Let's see what the main method is going to do. So they just spawn tons of threads. The more the better, and the more cores the better, obviously. Even if people like to have, thread pools, 1 million threads on 2 cores, but they are different problem, let's say. So in this case, what we can observe is that the foo method is being called by using B and C in different moment, and the goo the same. So what we are expecting is that both B and C concrete type and classes will observe in their secondary super cache value a ping pong between those types. And the output of the report is a human-readable kind of output because it has been made with the purpose of help a developer to fix it. So you can definitely copy, paste it inside the stack trace analyzer in IDEA, and just navigate to the relevant method. So let's just take a look at what the different part of it means. So overall is an ordered list of concrete types. The concrete types is the very first part that has received the highest number of invalidation of the secondary super cache. The number of invalidation are here reported, and later on you have the values that has been observed and ping-pong within a secondary super cache. And later, that's the very most important part that is, as I told you, compatible with the stack trace analyzer in IDEA. You have the call sites of the type check performed, and we know already was foo and goo, with which interface type has been tested against, and the number of time has invalidated the secondary super cache. This one is going to work with everything. That means class.isInstance, class cast, direct bytecode of cast, or instance of, or whatever similar to it, because we were using basically all in many of the libraries we have examined. And that's the most interesting part to me. So this method is actually so small, it's a production method. So we got it in few libraries. And we don't really are interested into how it triggered the problem. So believe me, it triggered it. But the thing that I challenge you is to tell me how many checkcast or typecast can you read? It's one, right? You bet it. It's not like that. Let's give you another hint. So if you look at the signature, this is a generic method. Generic method, you know, if you look at the bytecode, what it does, given that there is this generic type eraser thing now in the language specification, they actually they don't have a reified kind of generic types. They are enforced. How they are enforced? By introducing checkcast all the way down. So here, object required not null, given that it has a generic type, are going to have a checkcast that is a typecast against the context. That is definitely unexpected. It seems mind-blowing, but things are even worse now. And, you know, the report just works, but we already know that. What we would like to show you is even more horrible. Everyone has used list collection, right? And here, I can ask you the same things. How many checkcasts are you going to look at? Same problem, different form. So here, while iterating a list, you create an iterator. The iterator is generics. And when it's generics, you have an hidden checkcast as well. How bad can it be? Definitely pretty bad, you know, because you got lambdas, collections, iterator, utility methods, close the door now. No, really, it's terrible. I don't want to convince you to never write Java, because with Scala is even worse, actually. There are Scala people here. JVM hate you, believe me. But I can tell, as Sanne told, the JVM is a wonderful piece of engineering. So no panic. Just in time is very good to optimize it away, really. Unless type pollution happens. You know, always bad news here. But let me describe, by using the OpenJDK wiki, what means type pollution. So profiles are subject to pollution if the profile code is heavily reused in a way that diverge from each other. Clear? No, not really. I'm more confused. So let me explain you with an example that probably will work a bit better. So let's reuse the JDK reproducer code. In this case, for example, foo has been used by passing two different concrete types, B and C. In this case, the type check within foo, the instance of, has observed two different concrete types. In this case, we can talk about pollution. But if we are going to remove the second foo that was using C, now we got just foo that will observe B. In this case, the just-in-time is ensuring with the guard, with the type guard against B exactly, that you always use B. And if that happens, it's not going to perform the type check against the interface. It becomes a no-op, okay? And in this case, the just-in-time is capable to optimize it away. And the whole thing about the scalability issue won't happen. You know, it's magic. But how it relates with tech and power. So we talk about isolated and not isolated cases. Why it that matter that much? It matters because when you run singularly the tech and power test, they always trigger netty to use a single type. But gosh, they added a pre-validation step when you want to run the full test suite, given that we have endpoints that talk with the database that require netty to create a chunk at the response, HTTP response, that is another concrete type. And boom, it's going to make all the instance of to appear and the issue to appear. So it's definitely pretty bad. So what are, you know, the lesson learned is the agent is prone to false positive. It means that you can, you know, you don't know if what you see has happened for real. You just know that it's going to invalidate the secondary supercache. It's a bytecode level kind of tool. It doesn't look inside the, you know, the native class. No, the false positive are not that bad, actually. I talked with Andrew Dean, that is another JDK engineer, and I told him, I really would like to help a user and remove these false positive things. And he told me, no, punish user. No, it's not exactly what he said, really. No, it's a good guy. What he told me instead is that the false positive doesn't exist. There are promises of time bomb. So there are cases in which the false positive can become a real thing. And it's something that only the developer that have the domain knowledge knows if it's like that. Or if it doesn't know, it's better that it's going to be fixed. So if you fix everything, you are fine. No? So, please.
Yeah. So it doesn't look too bad because there is an open issue. And after we created a long list of libraries that we finally knew were affected, initially it was like, it might be an exotic pattern. Nobody is really using code like that, but after we showed them how many libraries and what's the actual, real-world impact, and could be your money, the bill or your cloud or your CO2 output that you're worried about, it's very significant output on the performance and efficiency of your system. So the JDK team seems to prioritize this more now. It was initially scheduled to be, fixed for Java 21, but the fix is really not that simple. So it's not really clear, when the fix will eventually land. So in the meantime, we have been fixing a ton of libraries that we believe are very widely used because we feel responsible for that. And you could definitely benefit from make sure you upgrade your libraries and your dependencies, because the differences in performance is not like in a single-digit percentage. Like we're talking about very significant performance boosts. And of course, if you maintain a library, or even your own code could be affected, the code that's running on some JVM library or framework, please use the type pollution agent to see where this is affected. But again, the number of false positives you'll see might be a bit concerning here. So it might have an impact on you. It might not. And some things we've seen that are very interesting is that, like, if you test things in isolation, so like if you run a single benchmark, which is having a very specific use case, you're not going to see, most likely, some of these problems. Because, for example, let's talk a little bit about like how Hibernate shows in this picture. The API of Hibernate is pretty much, persist or store or load some object. We have no idea what object that's going to be. So it's a type that the user has defined. And then we also do a lot of optimizations internally, depending on what type this actually is. So it's a lot of type checks, and it could be an enhanced object, which we bytecode manipulated, which means it will get an additional interface slapped on top, which we need to check for. So we can test, we can benchmark things on Hibernate specifically, and then we'll just, check for this single interface, and then everything is right. Because if you're testing for one interface consistently, all those types, you're good. There isn't going to be any flip-flop. The cache value is going to be stable over time. But now in a real-world application, what do you see is that, oh, that same object is first loaded via Hibernate, and then it's passed to a second-level cache, which is testing, is this serializable? Because we need to maybe serialize it to a different thing. At this point, that same object, which is your class, is being checked first for the Hibernate case by the Hibernate framework, and then it's checked by the other library for a different purpose entirely. And then maybe you're serializing it via Jackson or something, which is going to do some other type checks. Right? So the bigger problem is really you benchmark a single microservice or a single, micro benchmark. You're going to see certain patterns. But when you combine the many libraries in a more complex application, this pattern goes completely wild. So definitely need to check what's going on in your real scenarios, and that's where we don't really know what you're going to do, and you need to check yourself. Another thing we realized is, don't be too scared, because if you have this level of problems and you really can push your performance from 1 million something to 5 million something in a certain time, it means you are in a very good place, right? It means you really have nothing else happening in your system, and your system is already performing extremely well, and all the code you have is doing really well. We believe that most applications are probably not going to see these very wild scalability performance improvements because, honestly, we're all doing practical problems with business restrictions and time restrictions and resource restrictions on what you do. So you most likely have some other bottleneck already, which is going to be the dominant bottleneck in your system. This might help, but it might not give you as much worry as it gave us. So it was really fun for us to work on it on Quarkus because since everything was already super optimized, this was like the new bottleneck. And yeah, you can totally use the agent to, if you are already in a very good position, use the agent to get to additional performance improvements. We have, well, plenty of time for questions, 11 minutes. Any questions about this? We are ready for anything. Yes.
Please, microphone.
It feels like it is not, so if you, thank you for the talk, first of all, it was great. So what it feels like is that you fixed it in Quarkus and some other libraries, but it doesn't feel like a solvable problem. I think it's like N+1 problem that I don't believe that it can be solved. So I think eventually we'll spiral, right? So what do you think? What is your thought on that?
We can give. I can give.
Talk about the potential fixes, maybe. Yeah.
Yes. So there are potential fixes. One of those fixes are the one made by Netflix engineer, for example, that is to disable it. So no single cache. Because let's be honest. No, I'm going to say something bad, really. We can close them. No. The thing is that if you design something that have a single value cache capacity, how bad can be? You will ever do it in the real life? I won't. But they made it for good reason at that time. Their reason doesn't hold anymore. So the thing is that you can avoid it. The point is not that easy still, because people got workload that maybe benefit of it. So you can do it. The second thing is that you can use perfect hashing. So you won't use the cache anymore, but you don't need to perform a linear search among all secondary supertypes. And if you are fast to check it, you are fine. Why using a cache? And that's exactly what they are doing. There is,
it's boring.
Yeah, it's boring. But what doesn't make the things to be perfect is that perfect hashing makes the it to work. But if you won't find it, the slow path is to still search among all interface implemented. So it's no longer a scalability problem. It becomes a performance generic problem. And it's something that the people that talk about type, pattern, template, that thing, they didn't know that. But it's like that. So with interfaces, you are not in a good position from a performance perspective. Talking about, I don't feel it's solved yet, I fully agree. But I can tell you a small story because we have, not plenty of time, but enough. The Netifix. The people, I'm a good friend with the committer, contributor, the maintainer of Net. And he told me, Franz, it's horrible. What I say next is, if something is horrible, you can make it worse. So the real problem is that if you perform flow control by using types that are entirely in the hands of the final user without knowing what they're doing, you are not just using right that tool. And when I talk with Andrew Halley, that is one of the JDK leads, he told me very, simple, Franz, that's horrible. You folks do things like that with my Java? And I say, not my fault. Maybe, probably, but let's see. So I hope you are satisfied with the answer.
Yeah, there is one other angle to that as well, which is, while we were sending pull requests to all these projects, in some cases there was a bit of resistance. In some cases it was, my own project, so I can do it. For sure, like on the Hibernate side, I remember the first attempts of fixing it on Hibernate 5. I wasn't very happy with how the code was looking like, and it was certainly arising doubts about the maintainability of that in the long term. But also, while exercising this thing and fixing other libraries in the meantime, then I eventually got back to the Hibernate fixes, and we created some patterns. And I actually think that the new code that we have which is now in Hibernate 6 and works around most of these problems, we haven't actually done with fixing all the cases, right? But we fixed all the most significant performance bottlenecks. I'm actually pretty happy with how the latest patches look like. It feels pretty good, and so it also forces us to, critically review a bit of these patterns and code. Like, why were you doing this to begin with, right? So I think the report was super fun for us because now, of course, it's always nice to see that with 3 lines of code changes, you double performance of a system. That's fun. But also it forces us to critically rethink some of the design choices that we had in the code. Now, of course, if this is affecting, just iterating a generic list, that's very concerning. But what we also noticed is really the just-in-time optimizer can do really smart things. So we might have gone a bit fast on the type pollution aspect, but what happens really is like, say you're allocating an array list, and then you're passing this to a method which is accepting a list, not an array list, so the interface. And then within this body, it's doing some checks about a type. But this method is always ever seeing just the array list. What the compiler is actually doing is going to assume that this is always an array list. And those type checks are actually removed from the assembly that's generated. The only thing that it puts in there is, how the JIT compiler works. It will put a trap in there to verify, if some assumptions that have been made about the compilation decisions are wrong. It will, throw away the compiled code and recompile it again a second time with folding into the new information it had. Right? So in many, many cases that we have observed, what the tool actually describes is a false positive. Right? So we know from the bytecode that there are type checks in the bytecode, but that doesn't mean that there actually will be a cache invalidation in the actual code. So yes, lambdas are affected, and we have seen real lambdas that trigger the thing, but the majority of lambdas will not be actually a cause of concern. Right? The pattern structure is a bit more worrying because it's intentionally designed around the fact that you will be testing across multiple interfaces. Right? So that's a bit different. But yeah. So I hope that's a good answer. Other questions? Sorry.
The problem is that it won't be backported. That's a big concern because even if many people in the Java land will tell you, let's move to Java, go tell your manager. So I don't think that everyone is that happy. Things should be improved, but it's not easy. So in the meantime, what you can do, or wait, sit and suffer, or suffer and do something. So in this case, better the second.
Other questions? Yeah.
Do you know if languages like Kotlin have the same issue, or if they've managed to avoid the issue because they have that extra level?
They're all very badly affected, and sometimes even more because these additional languages, like especially Scala, we know is extremely affected because they build on top of the existing bytecode with additional constructs, and often they might require these patterns because it might not look very nice in your Java code, but when it's framework or generated code, it's more prone to create such things. Yeah.
And now let me anticipate maybe a possible answer, but Graal is affected. Just to let you know, because the class thing used is the same. It won't change. So.
Any other question? Yep.
Yes, hi. Thank you. First of all, really nice talk. Seems like a bit of a detective story, yes, which is quite enjoyable. Maybe a strange question, but I was wondering, why did you fix it in all those frameworks? Because the bug's been there for years. Nobody seems to be that bothered by it. And if the JVM people are going to fix it anyway, then why fix it in all those frameworks, especially if maintainability of the code becomes less because you have to do weird stuff with the code?
Excellent. So Quarkus is a combination of many libraries, and all of these libraries are part of Quarkus. And yeah, we wanted to really be fast and light and efficient.
Now, no, maybe in the future. Yeah. That's the thing.
And Francesco actually sent pull requests to other projects as well, just to explore the thing. Like we
they hate me. Banned.
Yeah. Anything? No? Okay. Thank you very much.